you need to have some knowledge and familiarity with some of the techniques that are used by organic chemists when they're preparing compounds from other compounds. So some of this you're already quite familiar with. One of them in particular were the two different kinds of heating methods that we used when we were looking at oxidation of alcohols. So remember that if you have a primary alcohol and you oxidize it with aqueous acidic potassium dichromate, you have two possible outcomes. So if we take ethanol, for example, you could get two different oxidation products. One, if you just oxidize it once, you can turn it into ethanal, which is that. But if you oxidize it twice, so first to ethanal and then oxidize further, you can turn it into ethanoic acid. And you need to know the techniques that you can use either to get this, if that's what you want, or to get that, if that's what you want. And this one was distillation. And the idea of that is that once the product is formed, it boils away out of the reaction mixture and you collect it somewhere else so that it's not exposed to any more oxidizing agent and it can't be oxidized any further. This one is reflux. And when you heat something under reflux, what you do is anything that vaporizes, you condense it so that it drops back down into the flask, back to where the reaction mixture is, so that the oxidizing agent keeps getting another go at it until it's oxidized it fully. So you need to be familiar with those ideas, but you also need to be able to draw the equipment. And it's important to practice drawing these things and to know what the expectations are, for an acceptable label diagram. So if we do reflux first, you have your flask, and your flask should either be a pear-shaped flask, which looks like that, or a round-bottomed flask, which looks like that. They won't accept a conical flask for these organic methods. Okay, conical flasks are good for methods that depend on sitting on the bench and things like that, but they're not good for this controlled sort of heating method. So you've got to use one or other of those kind of flasks, and you've got to label it. Okay, so either pear-shaped flask or round-bottomed flask. And that's where your reaction mixture goes. So again, it's a good idea to label that. You can put anti-bumping granules in there. They don't usually expect you to do that, but that's good practice because it makes sure it boils smoothly. Now the crucial thing in reflux is that as soon as you start heating it, these reactants are likely to start to vaporize, and if there's a solvent, then the solvent they're dissolved in is likely to start to vaporize, and if you just have an open top like that, it'll all just disappear into the air, so that's no good. And so what you do is you put a condenser on the top. So when you draw this, what you're drawing is a cross section through that, as if you'd sliced the whole bit of apparatus down the middle. And so what you don't have is a boundary there. Okay, because what you want to show is that this is a continuous tube so that the vapours can go up from here into there. So make sure you don't draw boundaries there, otherwise it makes it look as if this is kind of not connected to that, and that would obviously defeat the object. So you just draw a nice continuous tube going up through there, and then around this tube you have a water jacket, which you can draw like this. And the idea is that you put cold water through there, flowing continuously through the water jacket. So what that does is that it keeps the inner surface of this tube cold, so that any vapour that comes up here just hits this cold wall here, condenses back into liquid and drips back down to where it came from, and it doesn't therefore get lost. And that's the whole trick. So you need to label this bit of equipment. You can just call it a condenser, sometimes called a Liebig condenser after the guy who invented it, but you don't have to know that name, just a condenser is fine. But what you do have to do is show that the cold water goes in at the bottom and out at the top. If you do it the other way around, it doesn't fill up the condenser properly and doesn't work well. So they expect you to know that the cold water goes in at the bottom and out at the top. and obviously then you heat it from underneath. You don't have to draw the Bunsen burner and everything, just label that as heat. So that's one to practice. Make sure you can draw a reflux setup like that. Now distillation uses similar equipment, but it's a bit more complicated, because this time what you want to do is to condense your product somewhere else so that it's not going to drip back into there. So again, you start with a pear-shaped flask or a round bottom flask. So we'll do a pear-shaped one again here. And this time you have, again, a continuous tube coming up here, but now you want to have a side arm coming off it just as a bit of an angle like that. And then in the top of that, what you conventionally have is a thermometer. So you have a bung in the top here, and then you have a thermometer like that. And that means that you will be able to tell the temperature of the vapour that's reaching this point and then coming down there, and that should coincide with the boiling point of the material that you're condensing. If you didn't put the thermometer there and you just had a full bung there, it would still work. You just wouldn't know what the temperature of the material boiling over was. But if you just left it open, so if you just had this, that of course is no good, because the vapour is just going to go straight out the top and you're going to lose everything. So one way or another it's got to be closed at the top there. So the easiest one to remember is just put the bung in the top there and then draw the thermometer like that. Okay, so again your reaction mixture goes in here and you're going to heat from below. And your condenser this time is going to be attached to this tube, so it's coming on a bit of an angle down like that. And the angle is important, because what you want is that as vapour comes down here and turns into liquid in the condenser, it will roll downhill and be collected over here. So if you draw this at an angle going upwards, it's not going to work, obviously, because the stuff would then have to roll uphill. So the angle here is important. Okay, so you have a tube coming down here, and you have your water jacket around it as before. And then you can either just have the product dripping off the end there, or you can put some kind of delivery tube on the end. I'm not going to be too worried about the detail there, but you need to have some kind of collecting tube to collect the product as it drips out the end of your condenser there. So again, label the condenser, label the pear-shaped flask, and show which way the water flows. Okay, so the cold water goes in at the bottom and out at the top. Okay, so that's a distillation setup, and you can hopefully see how that will work. That stuff is going to evaporate from here, it will come up to there, and instead of dripping back down here, it will now condense there and it will roll downhill and be collected over there. And it works in this case because the aldehyde is quite volatile, because it's not a hydrogen bonding compound unlike these two, so it has a lower boiling point than these, and that means it vaporizes as soon as it's formed, condenses here and rolls downhill. You collect it there. You can also use distillation, of course, as a purification method, because if you have a mixture of liquids here in your mixture, they will boil at different temperatures. So if you heat it up very gradually, then the most volatile ones will boil first, and you can collect them, and then you wait and the temperature rises a bit more, and then you collect the next one, and then the next one, and so on. And that's called fractional distillation. Okay, so it's important to know that you can use distillation as a method to separate organic liquids from one another, and indeed from non-volatile stuff that may be mixed up with them as well, but based on differences in boiling point. That's where the thermometer comes in really useful, because you then know what the temperature is of each fraction as it boils across. When you make an organic liquid compound, the actual purification process generally involves more than just the distillation. That's often not going to be enough to get the pure compound, and you need to know about some of the other things that you can do. So many organic compounds are not soluble in water. You know that because unless they've got a hydrogen bonding group like an OH or maybe an NH2, they can't form hydrogen bonds, and therefore they won't dissolve in water. But they're often made in reactions which involve aqueous reagents. So for example, you might start with cyclohexanol, which is that, and you know that if you heat it with concentrated sulfuric acid, it will dehydrate, and you will get cyclohexene plus water. And that's a standard way of making alkenes. It is the way of making alkenes that you learn about at A level. But of course, when you do that reaction, what you end up with is this is a liquid, but it's going to be mixed up with your concentrated sulfuric acid and with the bit of water that's in there plus the bit of water that you formed during the reaction. So you don't immediately get pure cyclohexene. Now you could purify it in principle just by then distilling it off from the reaction mixture, but it's much better to get rid of this concentrated acid first, partly for safety reasons, but also because that in itself is volatile. So if you start heating it to try and vaporize this, you might start vaporizing the sulfuric acid, and that's not good. So you have other techniques which you can use for removing acid. So neutralization of a reaction mixture is quite important. If you've used either acid or alkali in your preparation, then neutralizing that is important to sort of protect your product once you've made it. So in this case, what you would do is use a separating funnel. And a separating funnel is a bit of equipment that you need to know about. So we did this in the practical when we made a chloroalkane from an alcohol, but that's, I think, the only time you've come across one. So a separating funnel looks like this. Okay, so you have this bulb thing here with a stem on the end that has a tap on it, like that. And there is a stopper that will fit in the top, like this. So that's a separating funnel. And the idea is that you pour your reaction mixture into there, and because this is non-polar, it won't dissolve in water. So if you add some water to your reaction mixture, you get two layers. Okay, so you get the cyclohexene, because it has lower density, goes on the top, and then this is H2SO4 diluted with some water that you've added. So you've got two layers like that, but you can only use this kind of method, obviously, if the product you're making is insoluble in water. If you were making an alcohol, this wouldn't be any good, because the alcohol might dissolve in the water and you're going to lose your product. So this is for substances with low polarity only that you can use this method. Okay, so you put them in there, and basically you just turn it upside down. So if this is your separating funnel with the stem on the bottom, you just put your bung in the top, shake it up like that, open the tap when it's that way up to release some pressure, and then turn it back the right way up. And that will mean that any sulfuric acid that was dissolved in the organic layer should make its way into the aqueous layer. So you're getting rid of sulfuric acid that's dissolved in the organic layer by doing that. And then you simply take the stopper out the top and you remove the bottom layer. So what will happen after you do that is that you end up now with just the cyclohexene layer left in your separating funnel, and you collect the aqueous acid down here. Okay, so you need to recognise this bit of equipment as a separating funnel and explain how you could use it to separate two liquids which are not soluble one in the other. Now that hasn't actually neutralised it. All that's done is removed most of the acid. To neutralise it, you do the same thing, but now you add an alkali, and you usually add something like sodium carbonate, which is a very gentle alkali that isn't likely to attack your compound. I mean, this is not a very problematic thing, but if you're making something with functional groups which could react, you don't want to add something really kind of aggressive like sodium hydroxide. So sodium carbonate's a nice gentle alkali, and what that will do is neutralize any remaining acid that you haven't managed to get rid of. So you get the same thing again, two layers with your cyclohexene on the top, and here this is the aqueous layer at the bottom, and any acid that was remaining in the cyclohexene at this point is going to react with the sodium carbonate in the aqueous layer and end up forming a salt dissolved in the aqueous layer. So you then just do the same as before, you just remove that bottom layer and you're left then with your purified cyclohexene on the top. What you then normally do is wash with more water, that's just to remove the last traces of the sodium carbonate and stuff that you've added. So you're just repeating the process several times, running off the aqueous layer, adding more water, shaking it up, running off the aqueous layer. So you wash with more water, and then finally you collect the organic layer in a flask. Okay, so having run away your last aqueous layer, you'll just have the organic layer left in here like we had at this stage, and then you run that into a flask. And the problem at this point is that it will still have traces of water in it, because obviously you've been washing with water, and so it's not going to be completely dry, and you want to get rid of the last of those traces of water. So what you do is you add an anhydrous salt, and in principle you can use any anhydrous salt, and the important thing about anhydrous salts is that they tend to be very thirsty for water, and so they will remove any water that's left in your organic layer, and it becomes locked up in the solid. So that's the beauty of it, that it is easily going to be separated then because it gets locked up in forming a hydrated solid. So you can use various ones, but the ones commonly used are magnesium sulfate or calcium chloride. Either of those would be fine. And that removes traces of water. So it's a drying agent. And then all you have to do is you then just decant the organic liquid into a flask for distillation. You know, so into a round bottom flask or a pear-shaped flask ready for distillation, which is going to be the last stage of your purification. Decant just means pour it off carefully, leaving the solid behind. What you tend to find is that the crystals stick together, the crystals of the solid, they tend to stick and clump together in the bottom of the flask, and that makes it very easy to just pour the organic liquid off. And then you're good to go. So you can see that this is quite an involved process, but the most important thing to remember is, first of all, the use of the separating funnel to separate an organic liquid, so long as it's a non-polar one or a low polarity one, from an aqueous layer. The use of aqueous alkali like sodium carbonate to neutralise excess acid. The use of an anhydrous salt to remove traces of water. And then always distillation at the end is the preferred way to purify an organic liquid after all those preliminary steps are done.